Okay, folks, welcome back to BFI 12. Now, we just talked about the network optimization, what it is, and what are the different kinds of problems that we face in network optimization, and how it affects your personal day-to-day life, as well as some of the areas where it is applied in the industry. So, what I would like to do is I would like to now next take the minimum cost flow problem. Okay, so here we are looking at the flow of materials or people from one place to the other place, and we want to do that in a minimum cost way. So that's why min cost flow problems. Okay, now here I draw your attention to one of the problems that is the problem 6.3 in your problem data set. Now the scenario here is there is a factory that uses these boom boxes that these three vendors produce, and the factory has two warehouses. As and when it needs the boxes, it withdraws from its warehouses and uses in the final assembly. Okay, so the cost is each vendor, for a set of 1,000 boom boxes, they charge $22,500. Vendor 1, vendor 2 is $22,700, vendor 3 is $22,300. But unfortunately, so these vendors are located in different parts of the U.S. and likewise, so their distances are different from the warehouses where the factory has. For example, vendor 1 is about 1,600 miles away from warehouse 1 and 400 miles away from warehouse 2, and likewise we have the detail for the other two vendors. Now, anytime that we basically bring the consignment from any of these vendors, the shipping company, the trucking company charges $300 flat fee, then 40 cents per mile, okay, as the variable cost of transportation. And so, we have these different rates for different vendors from perhaps different trucking companies. And so the total cost of shipment then would be, just the cost of shipment would then be $300, that's a flat fee, plus 40 cents per mile times 1,600 from vendor 1 to warehouse 1. Then for warehouse 2 it would be 300 plus 40 times 400 to warehouse 2. So that is the cost information that we need to get. Okay, but what we want to minimize is the total cost of procurement, not just only the shipment, but the total cost of procurement. That includes the purchase price as well as the shipping cost. So that's the total cost is what we want. Okay, now from each time that a factory needs, it draws it's from its inventory that's in warehouse 1 and warehouse 2. Okay, so that shipping cost is $200 per shipment. Okay, from warehouse 1 to factory 1, and likewise $700 from warehouse 1 to factory 2. So this is a distribution network schematic representation. Each vendor can supply about 10,000 boom boxes. Since we are working in terms of the thousands of units, I will just use 10, 10, 10. So the total supply in these three places is, from all these three places, is 30,000 or 30 units of boom boxes. Factory 1 needs 10 and the factory 2 needs 6 on a monthly basis. So that means we need only 16, but we have a total capacity of 30. So this is an unbalanced problem where the supply exceeds the demand. Okay. Now the distribution network basically says vendor 1 can supply to both warehouses, likewise vendor 2 and vendor 3, and both warehouses can supply to both of these factories. So this is the distribution network. On top of that, the problem also states that there is a shipping capacity on each route. So that means vendor 1 can send at most 6 units from V1 to W1, at most 6 units from V1 to W2. If it ends up sending all 10, so it is going to be a combination on this route that will sum up to 10. Okay, but nonetheless on each route he cannot or she cannot supply more than 6. So we have the shipping limitations as 6 on each one of those routes as the problem states. Okay. The next one is to go and then capture these flows. So from, okay, we have the arcs going from to. Okay. So from to. So let's just call V1, V2, V3 as 3 vendors, W1, W2 as warehouses, F1 and F2 as the factories. V1 to W1, V1 to W2, V2 W1, V2 W2, and likewise, I have this over here. Okay, now here is the how many units to ship, so that's going to be our decision variable. We don't know. The total cost, as I said, is going to be a combination of the purchase plus the total variable cost. Okay, now here is where I have the variable cost. For example, from vendor 1 to W1, if you look at it, it's going to be $300 flat plus 40 times the distance. And that information is what I have here, 300 plus 40 cents times, that is 0.4 times the distance, and we get that one. So here I have the miles, again, taken from the earlier table that I just pointed to. So the next is to get the variable cost of transportation from V1 to W1, V1 to W2 is there, V2 W1, V2 W2, and then V3 W1, V3 W2 based on the flat as well as the cost there. Okay, then the fixed cost here is, this is the cost of procurement. No. This is the cost of procurement. This is the cost of procurement, that we have. Vendor 1 for 1 unit or 10,000 boom boxes is 22,500. That's what we have here. The total cost then is the sum of the cost of procurement and the sum of the transportation. Actually, this should be the transportation cost. This should be the procurement cost. So let me just go and then change this as the transportation cost. Of the shipping cost, and this as the procurement cost of the purchase cost. Okay, purchase cost, and the total cost is sum of the purchase plus the transportation cost. That is that there. So we need to get that for each one of them, and so I'm going to post this on the website for you to get each one of those formulas, but that's how we get it. And so that's the next step to do, is to get the transportation cost. And of course we had to list down what is the shipping capacity on each one of those routes. That is 6 units each, so that's a column that we have here. Okay, now the next one is to get the flows. Okay, so whatever that flows out is going out, let's go with a positive sign. Okay, well, let's go with a positive. Whatever that comes in as a negative sign. Okay, as a negative sign. Okay, now in this problem we have a total supply of 30 units, total demand of 16, so that means we got 14 extra. Now as a management decision, if you want to get this 30 but use only 16 and hold back those 14 as a combination at these places, we don't know what is the best way, the problem would tell us, then in that case, so we can put that as the supply or demand over here. Now I did assume that since the problem does not say that we are going to hold back units at W1 and W2, and it did not say how many, what is the maximum capacity, I just chose it that whatever that comes in should go out. Okay, from each one of these warehouses, whatever that comes in should go out. In that case, the net flow out of warehouse 1 should be 0, and out of warehouse 2 should be 0, because this is what comes in and should go out. Okay, now what is the maximum that V1 can send is up to 10 units. Okay, that's why we have this less than or equal to 10 units, 10 units, whereas when you take this factory 1, it has only material coming in, so as per our notation that is negative, so that's a negative 10. Okay, and that is an equality, meaning that since if you put that as less than or equal to, the problem will give you 0, because you want to minimize the cost, so the best is not to send any units at all. So it should be equal to or greater than, you can if you want to. So this is going to be 10 units, that's going to be 6 units, but with an equality sign. So here we have a mixed over here. Okay, now so what we want is whatever the thing that flows in, that flows out. Okay, that means V1 W1, then V1 W2 should be that, and from then you go down here, W1 to F1, W1 to F2, W2 to F1, W2 to F2. So the net flow then is going to be, that's how we basically take the net flow. Okay, now what I would like to do is I would like to define the range names. Now for example, which I already have done, so what you could do is, like for example, from, to define the range names, what you could do, there are two ways. One, you can just block this, then go here and type the name, what you want to call that range name. Or there is another way, is to go and then select the entire thing, then go through the dialog box. I would like you to refer to the naming of the ranges in the tutorial that I have sent, or you can take any book on Microsoft Excel and learn from there how to name these ranges. Okay, range naming is a convenient way over here. So the best way, the most simplest way, is to go highlight the range and type the name. Okay, so like here I would highlight all this range, go and then type in this box from. Okay, likewise there is another range name that I have given, and this is 2. Okay, 2. And the another range name is the decision variable, which is the ship. Okay. And then if you look at here, you basically see all these range names from, to, ship, and the other one is the total cost, is the other one range name that I have. And so if you click onto that one, that tells you this is the total cost. Okay, the total cost is that one. Now once we have that one, now we want to get the relationship. Those relationship is the amount of material that is sent out of vendors should be less or equal to that, and the amount that comes into W1 and W2 should also go out. So that's that W1, W2 net flow, and whatever that comes into F1 and F2 should be equal to its demand. So that's what we have. So this is how we capture the model relationships. And of course the total cost over here is a sum product of how many units you ship from V1 to W1 times the total cost on that particular route. Okay, so that is the total cost of shipping. What we want to do is we want to minimize the total cost in such a way that these relationships are maintained. Now we have to get the relationship now here in terms of the net flow. Now if you do this, this is the command that I have, is sum if, okay, from J33 ship minus that. Okay, and this is a common command or the formula that we use, then we just copy them down. What does it say? Sum if, meaning that go from this list, from the list that we have here. J33 is what is here in J33 V1. In other words, go to the list from and only take the V1 from the list, only V1 from the list, and go and then sum those, basically how much gets written here from V1. So those are the two places in that case it is going to be. Okay, and that is ship. Likewise, since we are talking about the net flow, this is going out and this is coming in. Of course nothing is coming in, V1, V2, V3. Okay, so this is going to be 0 there. But if you look at W2, then that W2 would be whatever that comes into W1, W2. Let me go down to that and discuss with respect to that. Okay, now here, sum if from. Okay, go to the from list and then take J36. J36 is W1. Go and then take only those W1s. Okay, these are the two places. Sum what basically goes out in these two cells here, that is a ship. Okay, look into that one. This is going out. Now minus what is coming in, sum if. Now come to the two list, that is W1 here, W1 here, W1 here. So take that from the two list and W1, 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 look at the corresponding ship cells, add them up. So this is what comes in should go out. What comes in minus what goes out. Okay, so that is that command. Okay. So once you have that relationships, then just copy the command down to all the cells. Now go highlight that, go to the solver, data solver. Now solve. What we want to do is we want to minimize the total cost, minimize that, subject changing cells are my shipping, how much that I want to ship. You can highlight the range or you can just type the ship. Okay, add the constraints. The constraints are, okay, the amount that you ship on each one of these route first has to be less than or equal to the capacity on that route. Okay, so that is the shipping capacity on that route. Okay, so that's one set of constraints. The amount that you ship has to be less than or equal to the amount, the capacity on that route. Then add the constraint. That constraint is this net flow. The first three are less than or equal to, so block these three. That should be less than or equal to the amount that goes out of the vendor should be equal to or less than their capacity. Add. Then now the next set are equality constraints. So let's just go block all of them into one, equal to that. Okay, now we got the relationship. The amount that we ship has to be less than or equal to the capacity on those routes, and the supply and demands of these vendors, warehouses, and factories need to be satisfied. Click OK. Options, linear, non-negative. Click OK and solve. Okay. When you solve found a solution. All conditions are satisfied. Click OK. Now what does this recommendation say? The total cost of shipping is $374,460. So vendor 1 is not going to supply any shipments to warehouse 1, but will send 6. So that means out of 10, vendor 1 is going to supply only 6. Vendor 2 is going to supply 6 to warehouse 1 and nothing to warehouse 2. All 6 will go to warehouse 1. Vendor 3 is going to supply 4 units to warehouse 2. In other words, warehouse 1 will receive 6 units and warehouse 2 will receive 10 units. So 6 and 10, that is 16. And warehouse 1 will send all the 6 units to factory 1, whereas warehouse 2 would send 4 units to factory 1 and 6 units to factory 2. So this is the minimum cost. And then if you were to change from this shipping route any other assignment, the cost is going to go up. The cost is going to go up. And this is the minimal cost. Okay, this is a minimal cost. And you can run a sensitivity analysis report on that one to see, which vendor is more cost effective, meaning that, let me kind of do that too. Let me go back to this problem. Solver. Solve. So if you go back to that cell, then do the solver, solve, and then click on sensitivity and click OK, you get the sensitivity report. And what the sensitivity report basically says here is, if you look at it, the first 3 cells, the first 2 are V1 to vendor 1 and 2, over warehouse 1 and 2. This is V2, this is V3. So look at here. So this is where you can save on the cost. Okay, we are not sending any from V1 to warehouse 1. Okay, final value is 0. If you basically decide to change that, okay, if you decide to change that, it's going to cost you about $240 more to ship on that route. Okay, so that's that reduced cost, what it means. On the other hand, we are sending 6 units from V1 to W2, warehouse 2. And here it is a minus 40, meaning that this is a cost efficient route. If we can go back and then if we can change the shipping capacity on this route from 6, let us say, to 10, okay, to 10. So that means for each 1 unit that you increase, you save $40 on the shipping cost. So that's that allowable increase that you see is, you save at the rate of $40 per unit for the next 40 units that you can increase on the shipping route. Likewise, this is V2 to W1, so this is more cost effective than that route. If you decide on upping the capacity, shipping capacity on a particular route, this would be a place to look into. So that's what this reduced cost here means in context of this problem.